On the test, there will not be anything about PODs, because remember the points of discontinuity. We're supposed to know that's like a baby step in the direction of, is it a vertical asymptote or is it a hole? And on Friday we talked about how if it's going to cancel, it's a hole, but we have to make sure we graph that hole. If it doesn't cancel, it's going to be a vertical asymptote. So if a rational function has a non-removable discontinuity, that meant it was not going to cancel. It's not going anywhere. That means the graph of the rational function is going to have a vertical asymptote at that x equals a, whatever it is. Those that will cancel are holes. And I went through and showed you how we could actually find where the hole is going to be. And that's really a good practice to get into. Instead of making the graph and then accidentally forgetting you're supposed to put a hole in there, getting a hole on the graph right away is usually a good idea. So if we have something like this, and we realize, say that x minus 1s are going to cancel out. That means there's a hole at x equals 1. So I would want to know 1 what? Well, to find that, what you do is actually do the canceling and see what's left. And then plop the 1 in there and see what you get. So 1 plus 3 would be 4, and 1 plus 2 would be 3. So we would know to go ahead and put a hole on our graph at the point 1, 4/3 we haven't set. That way we wouldn't forget to put it on after we graphed it. Because here's the problem. In the end, we're going to plug it into the graphing calculator because hyperbolas get really weird. And if we don't know that there's a hole, the calculator doesn't tell us that unless it lands at a perfect number, which is very rare. So we want to know beforehand. The graph of this rational function, f of x equals p of x over q of x, has a vertical asymptote at each real zero of q of x if p of x and q of x have no common factors. So nothing even cancel out there. If they do have common factors, well, then you get a hole. That's what all of this says right here. So now it also says if m is less than n, then f of x also has a vertical asymptote at x equals a. What are they talking about? Well, they're saying, what if? Big what if, by the way. You get that? Well, does that mean negative 2 is going to be a hole? Well, we got a problem. Because if we actually did the canceling here, it's not a hole. It's a vertical asymptote. So they're just pointing out that maybe something like that could happen. And you just need to think through it about, would it totally cancel out, or is it going to be stuck there as a vertical asymptote? So for problem 2, all we're doing is we're looking at this and saying, what are the vertical asymptotes for the graph? Not holes, vertical asymptotes. So anything going to cancel here? That means our denominator is where we're going to get our vertical asymptotes. So where are they at? Now, reminder, sometimes they'll be a little more involved down there in the denominator. So just remember, if you're having trouble figuring out what the 0 is for that one, slap a 0 down, and most of you can add 1 and divide by 2 in your head and say, oh, that's going to be 1. So they could be more involved. This one wasn't. Just, from your homework, you might get something a little more involved. Oh, that was all we did on that page? Wow. Well, then I'll get you a candy bar. Try those 3.
Yes.
Hopefully those of you who have gone and watched the video so you'll be able to contribute a little bit. Not A. What were your vertical asymptotes for A?
Oh,
There it is, vertical asymptotes. But when you get to B, the x minus 2's would cancel out. So that makes that a hole. So we just want x equals negative 3 for a vertical asymptote. And then the last one, you had to do a little bit of factoring first. And then you're going to see the x plus 1's cancel out. So if they cancel out, they're not a vertical asymptote, they're a hole. So this one doesn't have any vertical asymptotes. But here's what I want you to do with your partner. Find where that hole will be in this graph. Find the hole. U. Now what did we cancel out? What was the zero for? U. Yep. Yep. Whatever the zero is for. 1. You got it? What's the x value for what canceled out? Where's our hole? -1. Now you go to the cancel form, which would just be y equals x minus 1. And you actually put the -1 in there. -1 minus 1 would be -2. That's where our hole will be at. Now I know they just asked for vertical asymptotes, but I was a little worried that Friday was a long time ago because it was such a jam-packed activity-filled weekend with fishing opener and Mother's Day and everything else. So a rational function can have any number of vertical asymptotes. Depends on how many factors we see. But at most, we're only going to get one horizontal asymptote. And here's where things get weird. You know, we told you in the past that asymptotes are lines that you approach, but you never cross. Vertical asymptotes. Horizontal asymptotes, every once in a while, hyperbolas will cross them. Hyperbolas are strange little creatures. So, usually, a horizontal asymptote will work for part of the graph, but maybe not the whole thing. So what we do is we say, they're nice to know information, and it's good to know that for part of the graph it should work. But know that horizontal asymptotes might get crossed. They might. It just depends on the graph, because hyperbolas have a lot going on. So, how are we going to know? How are we going to know where the horizontal asymptotes are? It seems like we've used up all the math we could possibly do with these fractions. Yes and no. The one thing we haven't talked about is the powers. And what are the degrees of these polynomials? So to find the horizontal asymptote of the graph of a rational function, compare the degree of the numerator, m, to the degree of the denominator, n. And this book has them a little bit out of order, because usually how we memorize them is, if the degree of the top is less than the degree of the bottom, then it's y equals 0. If the degree of the top equals the degree of the bottom, then we get to use a little funky fraction. If those two degrees are the same, what we do is we use their coefficients as a fraction, and that gives us our horizontal asymptote. So in that case, it would be y equals 3/4. And then if the degree of the top is greater than the degree of the bottom, we don't get one, and we have to write no. So these are, right now, things that we memorize. And one of the things that we're going to do as we get to pre-calculus is try to show you why does this work the way that it does. So I'm going to take a little extra time here and show you why all of this works. Let's say we had this. And these you could write off on lines on the inside of it. And we don't want to memorize. You know, we want to know why this would have a horizontal asymptote or not. You know, that's what we want to know. So I invite you to think a little bit of calculus for a second and think, what we're doing is we're trying to see what's the limit as we approach infinity. Where's this graph going to go as we go to the right forever or the left forever? What's it going to do? So instead of doing x plus 1 over there, I think, well, what would happen if it were infinity plus 1? And on the bottom, what if it's infinity squared plus 3 infinity minus 5? What's going to happen there? And as we talk about limits, what I need you to think of is this. Right up on the top there, I have infinity plus 1. And we need to think this way. We are huge environmental consciously group here. And we decide we're going to save the oceans. And we walk up to the ocean and we're like, every day this ocean is receding. This is bad. You know what I could do? I could spit in it. And that'll make it bigger. And we spit in the ocean. Have we changed how much water is in the ocean? We've done nothing. A spit? It's the ocean. We've done nothing. It's nothing. This 1 is nothing compared to infinity. Infinity goes forever. That 1 has basically no mathematical reason for being there at all. Down here on the bottom, infinity squared, that's huge. The rest of this, spitting in the ocean. It's not going to make a mathematical difference at all. But infinity squared, think of the powers. So now I look at it and I think, well, if I just treat this like an x, it's going to say 1 over infinity. So as infinity gets bigger and bigger and bigger, this is going from, let's just say, 1/2 to 1/4 to 1/8 to 1/16 to 1/32. What is this getting closer and closer and closer to? 0. As a limit. So that's why if the degree of the top is less than the degree of the bottom, our horizontal asymptote is going to 0. That's why it works. Now, if we end up in that situation, like I said, where we have y equals 4x squared over 2x squared. Again, I don't care if there's other stuff behind it. This is the highest power that's in the polynomial. And I look at this and I think, okay, so if I replace it with infinity, what's going to happen to those infinity squares? They're going to cancel out. And there is our horizontal asymptote right there. And then, if the degree of the top is greater than the degree of the bottom, well, infinity cubed over infinity, what's going to happen? Infinity squared. That's never stopping. That's going forever. That's why we don't get one. This is the nut. Like I said, at the Algebra 2 level, usually we just encourage everybody to go ahead and memorize, but memorizing stinks. It really does. So if you can think your way through, what if this were going on forever? What would happen here as we're doing this? And again, you really have to think of it's a drop in the bucket. If you're working with infinity, a number like 2 means nothing. It just isn't significant mathematically. So that is what this thing says, but as if you were supposed to memorize all of it. And you still could do that. I mean, if you're thinking, this little over my head this year, I'll hang on until next year when it's explained, you can do that. Degree of the top is less than the degree of the bottom, y equals 0. If the degrees match, do the funky fraction. And if the degree of the top is greater than the degree of the bottom, then you don't get one. And you write that. So that's what you would need to memorize. Now, finding horizontal asymptotes. All based on degree. That's what it is. So I take a look at this and I see there's not a degree, which means it's a 1 for both of them. So they're the same, which means they have to do the funky fraction thing, but there's no number in front of the x. What is it? It is a 1. Y equals 2 is my horizontal asymptote. Go over to this one. Degree of the top. Less than the degree of the bottom. I can't help it. I'm thinking infinity right now. So if we did just have x over x squared, it would be 1 over infinity, which is y equals 0. But if you want to memorize, the degree of the top is less than the degree of the bottom, so it's y equals 0 for the asymptote. Down here, this little buddy has an x squared on the top and an x to the first on the bottom. Put an infinity in there and you realize this is going forever. This isn't going to stop anymore. This is infinity squared over infinity. Cancel 1 out, you still have infinity. We don't get 1. It's not approaching anything. It's still getting bigger and bigger and bigger because that's what infinity does. It just gets bigger. So, good news. 3 of them for you and your partner. So, our partners. Everybody has that?
Yeah.
Cool. B.
Y equals 0.
C.
None.
Not gonna happen. Got it. So asymptotes incredibly important when we're graphing. Holes incredibly important. But now we have both vertical and horizontal. It is. It's. If you just do them in order, then it's okay. Essential understanding. You can get a reasonable graph for a rational function by finding all the intercepts and the asymptotes. We will know exactly by the asymptotes where a graph is not supposed to go, and then by the x-intercepts and the y-intercepts where it is supposed to go. Now, like I said before, we do grab the calculator in the end to make sure everything's working out the way it should. But like it says, sometimes you will also have to plot a few extra points to get a good sense of the shape of the graph and keep going from there. So, when I see this monster, the first thing I think is, I gotta factor this. I need to see where everything is at.
Yeah.
Two numbers and multiply to negative 12 and add to 1. You recognize that bottom one right there? Difference of 2 squares. Alrighty, so let's start where we should, which is vertical asymptotes. We spent a lot of time on those. Anything going to cancel top and bottom here? So no holes, but vertical asymptotes of what? 2 and negative 2. And you can write x equals plus or minus. Alright, well, as long as we're talking about stuff that's not supposed to be on there, let's talk about horizontal asymptotes. The degree of the top is the same as the degree of the bottom. One. Again, you use the funky fraction when you have those two equal to each other there. So that's the stuff that's not going to be on our graph. We didn't find any holes. Now let's go after the stuff that's supposed to be on our graph, which would be the x-intercept and the y-intercept, if we get some. We just have to see. So the x-intercept comes from figuring out how we can make y 0. I'm not going back to the original for that one. I'm going to this one. There were a couple of zeros up here that were pretty obvious in this factored form. What were they? Negative 4 and 3. Now I double check that that's not going to make my denominator equal to 0, but no worries there because we would have had something cancel it once. Alright, then my y-intercept comes from putting a 0 in for all the x's. That's where I go back to this one. Because I say anything with an x is going to be 0, so those are gone. I'll have negative 12 divided by negative 4. Okay, that's 3. Now, we're going to want 2 colors. Everybody's sitting at a desk, which means everybody has access to a colored pencil, even if you don't have your own. I'm sure some of you have colored pens and pencils and that stuff. But here's what we want to do. Let's make the stuff that's not going to be on the graph, the horizontal asymptotes, the vertical asymptotes, one color. And then we'll make what we're supposed to graph something different. So if you want to use pencil for one of those, you sure could. We'll make it pop. So one color for all the asymptotes. Again, keeping in mind, vertical asymptotes, we better not cross those or we made a mistake mathematically. Horizontal asymptotes, sometimes they get crossed. There's probably going to be a part of the graph that doesn't cross that, but you know that it's possible. So that's my don't go here stuff. And now I change colors and I put the, hey, this stuff better be on here or I messed up. Those are all my wonderful little intercepts on here. So now I'm going to punt. What I mean by that is I'm going to kind of take a guess at what I think is going on with this this graph because it is a rational function and it is hyperbolic. So I think there's going to be a branch down here approaching these asymptotes, and I think there'll be another branch right here. Now, if the horizontal asymptotes work, then this should be kind of an upside down parabola on the inside here. It should be. But again, we would need some points. And what we don't want you to have to do is putz around all day by putting numbers in by hand. So we encourage you, and yeah, now I realize I should have said grab your calculator. So if you need to get up and go grab your calculator, do that. If you want to just watch on the TV.
I like watching TV.
Now, here's the problem with the graphing calculator. It needs to know that everything on the top gets done first, everything on the bottom, and then do the division. If you don't put those parentheses on there, you're not going to get the right graph. So we have to know everything in the numerator goes in parentheses. And everything in the denominator goes in parentheses. Denominator zooms
No, I'm not. You guys use that one.
So, would we have been that far off if we'd have just gone with our guess at what was going to happen? No, because this one actually used that horizontal asymptote. Now, warning, some of them don't. Some of them actually cross in that middle spot. You know, the two branches still use the asymptotes, but the middle we're just not certain of. So now what we would do is we would definitely go on the test to our table feature, and we would say, okay, I need some stuff to the left of -2, but you know what, I only really need 1 point because I already know what it's doing. So 1, 2, 3, if I put -3 in, that should be good. See what that is, and then I'll make it approach my asymptotes. So -1.2. And here's one of those moments where you go, yes, I did something right. What's happening at -2 that we get an error message? There's an asymptote. Yeah, we did something right.
We did it right, guys.
In the middle, I probably want to know what -1 is and what +1 is for that middle portion.
So proud of you.
And then maybe just one more point off to the right there. Let's see, we've got 3 on there, so let's go with 4. And again, we can see our other asymptote was also right. And we're approaching the asymptotes, but we're definitely not crossing the asymptotes. Now, would it have been terrible to do that by hand? No, but it would have been possible. You know, we've got the graphing calculator, so let's use it. That's what we're supposed to use it for. So, now, I know they didn't put this on here, but I want you to think about this, because I don't want you to forget Friday. Domain.
Oh yeah, I think it's X.
2 and -2. X can't equal +or -2. Those were vertical asymptotes. Now, the second, the horizontal asymptotes for the range, we do have to graph it first because, again, we're not certain whether or not it's going to cross those horizontal asymptotes. But it didn't. So where was it? 1. Yep. Where those asymptotes are, our graph did not go. So domain and range. Looking at the asymptotes to see what happened. Boom.
I think we're good. Okay. We end at 27.
Yeah, it's 8:16. What's going on with the clock?
Oh, that's dangerous. Yeah, like what if we would have just let a little bit too low?
Let's start with that one, Mark. Let's start with that one. And like I said, we're gonna just be doing review of 8.4 and 8.5, so, we'll be.
Yeah,
So,
let's see
will
that,
you
Eli.
want graph?
That's so good.
Eli, let's see it. I'll pay you a penny if you finish this class.
Really?